Hey everybody, if you've joined, this is another installment of the 3D experience for SolidWorks. We're gonna wait just a few minutes before we really get going here. As myself, a lot of times I'll join these calls a little bit too late. Running around in the morning, grabbing my coffee, doing whatever else I need to do. So we'll give a couple minutes here, but have myself, Greg Albrechtson, and Dwayne Sawyer on the call today, and we got a fun discussion that's going to be coming for us today. Dwayne's going to talk to us about some plastic injection molding processes, and we're gonna, you don't have to necessarily listen to me speak the entire time. So you're welcome. You don't have to listen to me the whole time. You're gonna listen to somebody else here. So yeah. I don't know, Dwayne. Do you want to introduce yourself real quick before we kind of jump
Sure,
into the meat of all this?
sure. Yeah, I joined Dassault um, back in 2012, um, after having lost my career job in plastics. Worked in a lot of different places over the years. I've worked for custom molders, captive molders, worked for companies developing products, and uh, it ranged everywhere from automotive to packaging to conveyor systems. This is just a broad scope of industries, and so I got to experience a lot of different kinds of manufacturing processes. I've been involved with uh, everything from design to manufacturing.
Yeah, cool. All
So
right. Yeah. So did you do like consulting work then with
yeah, I've done
product
some
design?
consult. Yeah, I've done consulting work, product design work uh, that served me well. I kind of had played around with that for a while, and then when I lost my job in 2009, I rather quickly got a job in consulting,
Yeah,
and
nice.
so I figured if nobody's going to hire me, I'll hire myself, right?
Yeah, you, that's pretty rare with inside of our organization. We definitely have a lot of very smart, brilliant people, especially in Somalia. A lot of people with advanced degrees, but having somebody like you that is has industry knowledge and so forth is so huge. I mean, you'll be able to relate to the users and what their actual no pun intended, but what their actual experiences are, and be able to deal
Sure,
with that.
right.
So um, anyway, with just with that brief introduction, again, everybody, thanks again for joining. Please remember to like and subscribe. It really helps us out. It lets us know that you like the content that we're showing, and all of this, and it lets us know that you're actually watching these. So um, thanks for that. So again, Dwayne is a plastics expert with inside of our organization, and along the lines of what we've been showing through the previous sessions, we're going through this process of creating, modeling, and simulating the e-bike. And today, what Dwayne's going to show us is he's going to go through a plastic component of the bicycle. He's going to take a look at the fender and go through that particular process of showing us, can it be made? How do we make it from a plastic perspective? And is it strong enough? Is it manufacturable enough? So with that, Dwayne, go ahead, and
Sure.
let's get into
Yeah.
the meat of this.
Well, I understand that you guys have prepared the bicycle. Okay, I'm getting some feedback here for some reason. I'm not sure why.
Yeah, I don't have it on my side, so
Okay. Then we'll just go with it. Okay, so I understand we've developed this e-bike in SolidWorks, and then going into the plastics application, it takes us into the platform, the 3D Experience platform. So what you see on the screen is this fender that is that's been created, and it's a relatively simple part. The from a plastic part design, you're looking for something that is um, uniform wall thickness is always a necessity. Uh, and in the case of this part, uh, the chances are very good that uh, the plastic goes into the part into what we call a gate. So you probably want to place the gate in an area like this because it's going to be hidden, won't be shown.
What's a gate?
The gate is just the entry point for the plastic to go into the mold.
Oh,
So
okay.
the
So that's like
so
where you would shoot it in or something like
yeah,
that.
yeah, yeah, yeah. So it's called injection molding, and so the plastic is melted and then injected into the mold, and the mold itself is kind of the negative value of what the part is. It's the absence of the part inside encased in a piece of steel. So that is the mold, and so you inject the plastic into it, and then all sorts of things happen. And so the advantage to having software to do this for you is that in the past you would just pretty much go by experience, or if, you know if it's the first time you ever did it, you're going to be in for a surprise. I mean, you put the plastic in there, and if it doesn't come out the way you expected it to be, it could be for a number of reasons. It could be the way it's processed, the amount of pressure that's behind the plastic stream
Yeah.
going in. It could be, when it cools down, it's going to warp because of some of the geometric construction of it, or it can be just the processing parameters that are there. So the software itself gives you the ability to predict
Yeah.
what your end result's going to be.
So that's kind of like our whole mantra, right? Is this the whole mod sim? Like,
Oh, sure. Yeah.
simulate it before you have to build it. Reduce all of that uh, testing and prototyping and everything that you have to do. Is like just do everything on the computer. You can do hundreds or thousands of iterations, and then just even if you don't get it right, on the software, if you can get it close, at least go through a lot of those rudimentary kind of things, and then then you can just build hopefully just one mold at the end and not several molds.
Yeah, and for a part like this, it's a relatively simple part. Um, it's going to have a curved parting line on it. It's going to have some complexities in mold making. But if you were to make one cavity of this, I don't know what it might cost. It might cost you $20,000, $30,000.
Okay, that was my next
Just
question.
just
Yeah.
just for a single cavity. Um, you
Wow.
could probably make it cheaper by making it out of aluminum or something, but then it won't last very long. But if you are um, so if you are doing something that's pretty complex and a multi-cavity, you can um, you know odd as it may seem, some of these small closures that you have, like on a water bottle, they make a very large cavitation mold, like 125 cavities or whatever, and there's a lot of parts in there, and
Oh, right.
you could easily spend over $1 million for a mold.
Whoa.
So it really makes it important to know what you're doing before you go into invest all that kind of money, because it's the repair or the modifications that might have to be done, especially for a multi-cavity mold. That would be crazy. So the process is typically you prototype it, in a single cavity, and then you might go to a pre-production type of a mold just to make sure you're thinking correctly. And then once you've got everything lined out, then you go ahead with the manufacturing of the full production
Yeah.
mold with multi-cavity.
Cool. Well, let's see how we do. Let's see how we do this fender. What do we? So we brought the part in from SolidWorks, right? So now we've got the part in
Right.
SolidWorks, and I showed in some previous sessions lots of different ways to do that, and the history tree and all that kind of
Sure.
stuff.
Sure.
So we've got the part. What do we do next?
Well, the next thing we do is we just go up here to our compass and just select the plastic injection molding app. And so this pops up with a window over here that allows you to kind of step through the process. So if you look at this, the first thing you see is the parts. And under this, you've got a couple things. You've got contributing parts. There's only one in this one. But if you click on that, you end up with a tree. And so we've got this part that we can say, okay, this is my plastic part. And so that's as hard as it gets right there. Now, if you
I
had
can
to,
handle that
yeah,
on a Monday
it,
even.
all right. So if you've got uh, multiple things you're considering, such as cooling lines and runner systems and that kind of stuff, it allows you to assign those domains to those different components. And you see the green check mark over here, and
Yeah.
I had opened this up before, so I had a material in here from before. But if I were to go into here, it brings up a palette of materials that comes with the software, and of course, and then I get this little thing here.
Yeah, yeah. We'll close our eyes.
Okay, okay.
We'll close our eyes while you enter that. So while you enter that in, you said the materials come with the software. So
Yes,
we
yes, they
get
do.
like a default handful of materials.
Yeah, if you call 4,000 a handful, yeah.
That's two handfuls.
Yeah, right. So um, the material that we use has to be you just can't go make it up.
Yeah.
Because it's characterized as being a non-Newtonian material. You need to understand the reaction of pressure and temperature on the flow of the plastic. And so uh, these materials that we have here are all been what they call characterized with that data, and it goes into we put into a material file, and so that's what we supply to the customer. We've been developing relationships with all the material manufacturers. We don't have them all yet, but we have a good bit of them, and are supplying us with that data.
So would
Uh,
I find them under like their brand names or just like General Nylon, or Delrin, whatever?
well, both. There will be if this will show up here.
Yeah.
But it will be under family type, like a nylon or polypropylene,
Okay.
um, or it will be by. So you've got these materials, and down here you'll see that there's plastic, there's ABS, there's
Yeah.
different types of plastic, uh, and so you would just go in and you can search for something that you've recently used. So if you're working on something, and this happened to be one I was running, one with cooling channels, uh, or in this session, it doesn't have anything because I haven't done anything yet. So,
Yeah. Yeah.
um, so you can actually type in here. Well, let's go back to this one, and so we've got some generic materials in here too. So we can just sort by something called generic, and it's going to give you 136 of them.
Awesome.
Um,
136 generic
yeah,
material. Yeah.
and unfortunately, some of these that I have in my database are duplicates. But
Yeah.
so you got them by family type. So um, high impact polystyrene, or you've got low density polyethylene, just a bunch of different ones. So if you were to go to the particular one you were looking for, you could then just select that, just whatever that material is. And this is a
Yeah.
nylon 6,6. And so you could just hit a right mouse click and say apply, and then select this, which I guess I can do that. Let's say apply. Um, and
So this is great. So these are all stored in the database. So I mean, it's just
right,
like
right,
it's
right.
that whole concept of one source of truth, right? So anybody with access to this cloud tenant has access to that exact material. So you don't have to recreate it and enter this in every single time. You can just
No.
grab it, and
What you
everybody has to use this. Yeah, everybody can use the same one.
Right. If you end up with a workspace that you work in, and you get a 3D XML file, and you import it into that workspace. So that's how you get access to it.
Cool.
You can have individual files that you could import as well, but
Yeah.
this way everything's there, so you can
Yeah.
choose whatever you want to do.
Nice.
So notice the green check mark is there. So I'll go on to this next one, which also has a green check mark. So that's just because I visited it before. But you see this area where they're in gray. These are the material properties that come in from the material I selected. So it's giving me
Oh,
melt temperature, it's giving me mold temperature, the ejection temperature, and that's the kind of the prediction of the manufacturer saying this is the earliest temperature where you should or can eject a part from the mold. So you eject a part from the mold before it cools down to room temperature.
uh-huh.
Because in injection molding, cycle time is money. So the
Oh,
faster you can,
right. So they got to get something else in there.
right? So fast you can make it, the more money you make. And that money, you may or may not have somebody sitting next to the machine operating it, but that machine costs millions of dollars, and they so you break that down to what's the cost of the hourly rate,
Yeah.
and all the way down to the seconds, and you know how much that's costing you per second.
Yeah.
So these can be edited. Is typically not advisable, but unless you really want to do that and need to know how to do that. So like melt temperature, sometimes melt temperature, you might increase the temperature if you've got glass fiber and materials that helps it to flow a little better.
Mhm.
Um, but in most cases, you're going to accept it. And for the beginner, just accept all the defaults and you're good. So the next thing you look at is, because so we're really kind of setting up a virtual machine here. We've got the mold sitting in a machine, and so it is already calculated for you what uh, the fill time should be. If you want to go in and change some of those, you can. You can set up a profile as to what happens when, what's the percentage of the flow rate, or by by pressure. There's a number
Mhm.
of things you do. Again, you can just accept this as a default. The switchover point from filling to packing um, is a default of 98%. Industry standards run anywhere from 90, 92, 94% up to 100%. But this is typically a well accepted number, the 98%. And so you can go in and change the packing profiles as well. So this shows you how you can taper off your pressure depending on your settings. But again, these are preset for you. So if you want to, you can just accept all those and run them the way they are. We have some other things that you can set. Now, in this case, if you've got a runner system attached to this,
Yeah.
um, and you've got identified, but the runner gets sheared off when the mold opens, it's part of your simulation, but you don't want to be part of your warp. So you just kind of eliminate that.
Yeah. So what's
Uh,
a runner?
a runner is the channel. Think of the uh, like a field you're going to irrigate, and so
Yeah.
you don't have water there. You get a couple ways of getting water. So one of the ways they do it is they dig channels and let the water flow through those channels and get to the plants where they need to be filled or
Mm.
water. So in this case, it's creating a channel by which the plastic flows through the mold to the cavity and fills the
Okay.
part.
So as a kid, I used to build model airplanes, right? So
Yep,
with those, like, I'd have
that
all the little parts I had to break off the
the
branch
runner
thing.
system. That
That's
was
a
the runner
runner.
system.
Okay. All right.
Yep,
All right. Cool.
yep, for
Got it.
sure. And it's interesting because that's the thing that you try to avoid. In most cases, you want to minimize the amount of runner system, and especially in
Uh-huh.
today's economy, you don't want to throw that away or regrind it.
Right,
Uh,
like, that was more material than the parts itself
exactly,
when I was a
exactly,
kid.
right.
Yeah, I
Yeah,
didn't know
so
what
that
to do with it either, right?
well,
Yeah,
yeah, throw it away is what you did.
yeah, that's what we did, yeah.
Yeah, yeah. But that's all recyclable. It's thermoplastic material, so it can be remelted and reused. Um, Plastic generally can be a rule of thumb is like 25% regrind without doing a huge lot of damage to the physical properties of the plastic. So, you know, minimizing a runner system will help you to minimize the amount of regrind you have. Because in today's world, those runner systems that you produce would immediately be put into a grinder, chopped up into little bits, mixed
Yeah,
back into the pellets and remelted.
nice. Okay.
So in this case, we we just click OK. Now the conditions that we're setting up here, we only have one, and it's a injection molding condition. So because these are show surfaces, you're not likely to have want to have a gate there. Now, the importance of that is that when you have a gate, the plastic inside that gate is still pretty warm. And so sometimes when your mold opens up and you separate your runner system from the part, it'll create a little string of plastic. And so that's something you don't want to see. And especially if it's a controller or something you got your hands on, you don't want to feel that little uh, piece that's left
Yeah.
over from the molding
So
process.
that's like if you have two gates and then you get where like that just shoots into the same place, you
Well,
throw your
that's no, no, it's a net line. So I'm just talking about the vestige of the gate. This
Oh, okay.
part. So it's kind of like if you you take like a candy kiss, the shape of them.
Oh, yeah, the little
And,
nubby
and
thing.
you get the little point at the top, and that's where
Yep.
it shut off the flow, and that's what's formed.
Okay.
So
Cool.
in this case, you end up with a little sharp, spiky thing that comes out of the gate. So
Right, right.
you try to manage where that goes, and so ideally, a part like this, you would place it in the very center of the part, which would be like right in here somewhere.
Hmm.
But that's gonna maybe show, and so you wouldn't want
Yeah.
to do that. So this is the attachment point where it's going to go onto the bike. So you click on there, and here's my gate icon, and it comes up and it
Nice.
says, okay, the default is 3 millimeters. Now, that might be a little large for this part, but it's again, you can accept the defaults and you can get a result just from the defaults. If you want to change that to a 1 millimeter gate, you can do that. Or if you've got a edge gate or side gate or whatever, you can actually change this condition here to accept a face. And so that cross-sectional area of that feature you've got will be represented here as your gate.
And that's basically controlling the the size of the diameter of like where the
Plastic goes in.
plastic's being injected in, right? So like a bigger one's going to shoot more in at once, and a smaller one's going to
Absolutely. Right.
get
Right.
a cool.
Yep.
Just a quick thing. Hey everybody, again, thanks everybody for watching through this. Please remember to like and subscribe so that you can be notified when we have these new sessions out, and you know you can follow along when we have that going. We're kind of about halfway through. Just kind of wondering if you have any questions. Please put some questions in the chat. Let us know if you have some questions. We want to keep this a pretty informal sort of presentation, as you've seen. We've gone through this, so just ask questions as we go through, and let us know if we can help out or redirect our conversation. You saw when I was doing my presentation, I went on a lot of side tangents and really came back. So let us know if you have questions. Thanks, Dwayne. I love this assistant panel, by the way. Really, I know structural simulation pretty good, but I don't know anything about injection molding. But with that assistant panel, I and having the material model in there, I could probably figure this out. It looks pretty easy, pretty slick for that assistant panel being there. That's
It
my
is. Yeah.
yeah.
So now we've added all the things we need to add for this particular one. So we're going to go into simulation. So I could do, if I had cooling channels, I could do this mold cooling analysis. But since I don't, it's grayed out. So if I didn't want to do these two, if I want just to check to see if I can fill it really quick, that's all I need. But for this one, I'm just going to run it. Now we can run as many as 8 cores, which is included in the software, so you don't have to pay extra for those.
Sweet.
So so I'm just going to click on this, and what's happening behind the scenes is actually creating a mesh. So you don't have to worry about the mesh. And if your model is clean and doesn't have any gaps in the model itself, it should create a mesh very, very easily. And so now we're off and running. We are actually running the simulation. Here we can see as it's running, there's a number of plots. If there's some error messages that come along the way, they'll show up
You're living
here.
on the edge running this live, man.
Oh, yeah, I know. But it doesn't take terribly long. So as it runs, you can see the flow rate as it's filling the cavity. And so anyway, we're partway through, but we can jump to the results. I have those done. So what we're going to see, I'll probably have to stop this, but I'm going to stop this and go over here.
This is the Julia Childs where now
Yeah,
you
yeah,
pull
yeah,
the finished cake out of
yeah,
the oven.
exactly. Right. So
Yeah,
here's the
nice.
finished cake.
Looks
Okay.
delicious.
Yeah. Oh, it is. It is. So you've got the pull down tab for each of the ones you have run. You got the fill simulation, the pack some and cool simulation, and you got the warp simulation. So the first one you want to look at is, because really the first thing you want to understand is, can I actually fill this thing?
Right.
I can go up here and click this little button up here, and it will do the animation automatically.
That's
And
cool.
remember, I said that ideally the gate should be here somewhere. And so now
Yeah.
what you're getting is this part being filled last. And in this case, it's probably not a huge deal, but you're probably going to get a little more warpage in this area.
Yeah.
So, but that's why we do simulation. Sometimes what you want to do, you really shouldn't do, and the things you shouldn't do, you really want to do. I mean, it's kind of one of those things.
Story of my life, man.
Right,
I
right.
guess you could probably move the gates like underneath because nobody would see them underneath too, right? So
Yep, that's true. And of course, in this case, you have to think about the mold design and that kind of stuff, because putting the gates on the other side will make the mold more expensive.
yeah. Oh, okay.
So
So when I'm watching this down there at the very bottom right, it doesn't look like the
it fills. I think that's
yeah.
just a,
Am I seeing that it's actually not filling down there, or
well,
I'm
I
just
think
going
it's
so
just a,
fast I'm missing it?
yeah, I think that's what it is. It's just a visual thing.
Oh, I saw it there. Yeah.
So
Okay.
so if
Cool.
I stop this, I can slide this over here, and so
Oh yeah. Nice.
so there's a plot for that. We can go in here and look at get down here to it. Come on. Oh, maybe I need to get out of this thing here.
Oh, because you were
So
still animating.
now I was still trying to animate,
Yeah.
in its top state. Okay,
Yep.
um, so there's a couple things in here. You can look at air traps, uh, and air traps are. I'm still animating. Why is it doing that? Uh,
I think you're up there in the compass. Just need to
oh
click on it
yes, you're
there.
right. You're right. Yep, you're right. Um, so you can look at ease of fill. Now this one comes up all green. So again, this is you don't have to be a rocket scientist to figure this out. That green says go, and yellow is cautionary, and red don't do that. So so had it been a non-fill down here, you would have gotten the red.
Oh, okay.
Now that also says, okay, you've got some stuff on a razor edge. And so if you got yellows and maybe even some reds, but it shows it fills, variations in your molding process you may find you're going to get some short shots.
Mm.
So to solve that, you might need to bump up the pressure, the injection pressure. You may need to change the wall thickness. You may need to change something in the flow path to make it flow easier. So there's, those kinds of very helpful things you can learn. You've got weld lines are hard to see in this particular one because the weld lines are where you were talking about before, where you got two melt fronts coming together,
Uh-huh.
and
Oh,
and
yeah.
so we're seeing them right here, and they're not very big. Now, had those holes been larger, this weld line would have been greater, and if they'd been rectangular or square, they would have been even bigger.
Okay.
But the flow goes around here, and so what you're looking at is you're looking at degrees over here, ranging from roughly 0 to 100 and 120, 130. So if you can imagine the melt front going around this hole, if you look at this line right here, which is the front of the melt coming this way, it'd be like represented by 180. It's a straight line.
Uh-huh.
As soon as it starts wrapping around here, and now you get this V-shaped flow, and so
Yeah.
it's that angle of inclination, I call it, the two faces, is where you get to understand the severity of the weld line. So
Yeah.
if you're at 0, that's a head-on collision, if you will. That's going to be your most severe weld line, and part of that is because the molecular chains in the plastic don't combine; they just bump up against each other.
Okay.
So as that angle increases, they're starting to commingle. The two flows are commingling, and then it becomes one flow again.
So that's like where they're
So
coming together, like straight on or something like that, rather than
straight
just
on. That's the worst case, is going straight on. Right.
yeah, yeah.
Yeah. So you've got you've got pressure at the end of fill, and remember this is the lowest pressure, and this was the
Yeah.
last to fill. So if we look at jump over here to the warp simulation. So we see in the warp simulation, basically we got higher displacement at both ends, and
Uh-huh.
there's even more here than is over here, which was borne out by the pressure at the end of fill,
Mm.
and that kind of thing. So um, right now I have this set up at this is displacement total. We have displacement vectors, and so we show those now, and so this is showing you the movement direction of the plastic as it cools. So these are the parts that you can export to a structural app or whatever. You can actually, from this information, you can get a deformed shape. And so you can then take that into using some of the tools that we have um, on the CAD side, CATIA in particular, the VSO,
Oh,
which virtual optimization. So we can actually say, okay, here's this deformation vector. This is our original geometry. Now morph this to look like the warp geometry.
yeah, yeah. So I've done that with simulation before. Like I've done like sheet metal or composite simulations, and then
Right,
I can take that displacement file. So this is the same thing. So this is a displacement file, and we
right,
bring that into CATIA, and using one of the shape morphing tools, you basically apply this displacement file to the B rep or to the geometry, and it morphs the geometry. So then you can go through this. That's cool. I didn't know you could do that with this, but then you could go through this whole iteration of, knowing what your final part looks like, and then, like with Springback, then you go through that loop. And
Right.
so sometimes when you design in the software, you don't necessarily want to design what you want your finished part looks like. You have to design what your mold part looks like, so
Exactly.
that when
Right.
it comes
Right.
out, it is what you
Right.
hope it is.
Right.
Yeah, that's cool. Nice.
And you naturally do that with shrinkage, and you kind of guess what your shrinkage is going to be. And with different materials, they're going to shrink at a different rate. So
Yeah,
what you do is the old way is you've just took a global factor
yeah,
percentage and just scaled everything up and say that's my mold geometry, and hope that you guessed right. And so when it cools down, it cools back to the as designed shape.
yeah. I'm
But
tired of guessing.
well,
I just want to know. I don't want to guess anymore.
but these areas that are showing red, they're
Yeah,
going to be moving more than you would have guessed for a global shrinkage.
yeah, yeah, yeah.
So from this, you can actually is it's possible to create um, the inverse geometry, not the shrinkage, but the expansion, if you will,
Yeah.
for the mold geometry. So if you were to expand this and then take the geometry that's been morphed, you can use that, machine it, you can make your tool out of it. Then if your software has done you a good job in predicting what that warp is going to be,
Yeah.
you can get closer to the as designed part after
Right, right.
after the part's injection molded, cooled down to room temperature, and ready to be assembled.
Yeah. Nice.
You can also look at this for assembly of parts. If you're uh, of some sliding parts or whatever that are part of an assembly, and a warp shape would be part of that. That would be cause some binding or
Oh, just
higher
like a
friction,
fit check or
or
something like that. So put
yeah,
this
yeah,
back
yeah,
in the assembly and do
sure,
like a fit
right,
check.
right, right. But this software is going to basically tell you the simulation of that injection molding process is as though you had built a mold, put it in an injection molding machine, ran some parts, and now you've got them. So it saves a lot of time and money.
Yeah.
And so the earlier you do this, the better off you are.
Nice. Cool.
So you've got this is a displacement. You can, if you really want to get kind of crazy, you can change this, exaggerate it, so you kind of see what's actually happening in your part in terms of warpage. But you know, typically the real thing is you want a one-to-one relationship with that, and so that's all adjustable.
Yeah. So that's just like a magnification
Yeah,
amplitude
yeah, yeah,
kind
yeah.
of
And
display
sometimes
factor.
if you got some slight, changes, it helps you to identify where those are. So here's in the packing cool, we still packing is most of the heat's been taken out, but your heat still resides here. You can check your temperatures just by hovering over a spot, and it'll give you that information.
Why would I
Um,
care about my temperatures in injection molding? I mean, what?
well, a while ago I mentioned the ejection temperature, and I
Uh-huh.
also mentioned that cycle time is important. So the kind of the old school way of thinking is that I've got a dimension of a part that I've got to maintain. And so you get some guy I've been a molder for 40 years. I know what I'm doing, and so what he does, he parks it in the mold longer.
Uh,
So that mold becomes a cooling fixture that you freeze that shape into your part. So it comes out, he measures it and says, see, I did it. Well, the problem is if you got an assembly, you're part of assembly that goes into, say, an automotive thing, and you're molding this thing in wherever, in um, a northern part of the country where it's cooler, and then but your assemblies are being done in Mexico. So you ship it down there, and some guy's driving a truck, and he stops in Tucson or whatever and spends the weekend doing whatever, and inside this truck, and it's really hot in there, so it becomes a annealing oven. And so any residual stresses that are frozen in by this molder now becomes released in the shape of excessive warping.
Ah, gotcha.
So in some plastics, it actually requires you to check the part 2 or 3 days later to make sure you understand how much it's
Uh-huh.
changed. But in the case of molded in stresses, it's going to you need to mold it with the least amount that you can do. So,
Yeah.
and that's all tied together with cycle time, tied together with dimensional stability. It's tied together with a lot of different components of that.
Well, Dwayne, I think we have about 5 minutes left. So, if what are you have some key things that you want to go over before we wrap things up, and maybe just we'll see if we have any other further questions at the end. But yeah, so show us the rest. I mean, we've gone through this. This looks, I mean, super simple. We've got a catalog of materials we can use. We've got the ease of just taking this geometry and putting your gates in different locations. Running the simulation, looking at some results here. Do you have what are your last handful of takeaways that you want to be sure people know, within the software, the capabilities?
Well, I think I've mentioned most of them, but I think it's the general thing is where you just really get an idea of, number one, what the part's going to look like. How does it respond to your version of the design? Because designers say, well, I just need a rib here, I need a standoff post there, I need this, I need that, without any consideration of what it's going to do to the molding of the part.
Mhm.
And so you can go through and uh, predict what those are, and if you need to make geometric changes, make a rib a little narrow or thinner, or make a do a different type of a standoff, you can do that. And then, of course, the process itself can all be done. Can we do the studies on the cloud? Absolutely. Um, these are done both on can be done on premise or on the cloud. Um, and then you can run some DOE studies if you've got want to look for the optimal settings. And you can even do some DOE studies on the geometry itself. If you can, rib placements or uh, gate locations, and to try to minimize your warp, whatever it might be, you can actually configure some studies for that to help you. Those
So
take some time, but
so
they're
so
helpful.
you mentioned DOEs. That's one thing we haven't talked about in any of the previous sessions. Is we have a product called part it's part design simulation that allows us to, or parametric design study that allows us to do designs of experiments where we can, from a structural standpoint, we can modify dimensions or material characteristics and have it propose what those particular solutions are, and then you can do a study. So um, you're saying here within inside of the injection molding uh,
It's not
utilities, we can do DOEs here as well.
it's not inside the software. You have to use you know other pieces of software to do that. But
Right,
yes,
right, right. You would use PDS, yeah, but you could
right,
change like your gate locations and different
right.
things like that. Wow, wow.
Yeah,
Speaking of gates,
yes.
go ahead, go ahead.
Well, I just see a question that came up about sharing the results. There are a number of ways to do that. There's a report that you can put out as either a PowerPoint or a Word document. I don't find those extremely useful because you don't see the 3D representation, but you can create a 3D file that can be shared with other people. They can mark it up. They can, you say, I noticed the fill doesn't do very well in this area or slows down in this area, and draw a circle around it and say, what can we do to change this? So those are things that on the 3D Play file that you can create.
Yeah.
So
And
there's a number of ways of sharing that data.
and I assume this is all stored, in the same tenant, so anybody with access can
Correct.
open this up, and they can visualize it as well. And so you
And
mentioned 3D Play. 3D Plays one of those cloud or those internet-based utilities where you don't even have to launch the software. You can just come in and take a look at the results.
yeah,
Right.
right. But if you were sharing it with a tool maker or whatever, you can export that to a file that you can share.
Um, Speaking of performance, we're running up against the end of the presentation, but we've got a few questions here that I do think we want to try to get answered. What about a structural simulation? Like, so now you've gone through the molding process.
Mhm.
Can I do a structural simulation, like a force loading of this plastic
Yes,
part now?
yes, you can. Um, with There's a couple of products that we have on the platform, structural tools we've got that will import the data directly from IME, or the injection molding engineer software, um, without going through a third-party translator. And so you're able to bring that directly into the structural app, and just apply your loads, and um, however you want to do that. So in the case of this fender, you might want to understand, will this thing break off if I hit it hard because it's plastic or whatever, uh, so you can assimilate that as uh,
Okay, so I can take this and all the material,
properties and stuff.
all the material properties from the injection molding will come over um, into the simulation, and then I can simulate it. Very cool.
Right.
Um,
Yep.
cool. So we do have another question here. Might be a tough one, but can you highlight the main difference? Why would I want to use the IME, as you called it, the injection molding here on the platform versus something in SolidWorks Plastic? Because SolidWorks also has some plastics
Correct.
capability there as well. Can you highlight some of the main differences between the two?
There aren't any. No. uh, the solver that's in SolidWorks Plastic is the same solver that we have in the injection molding package on the platform. The difference is, in some ways, the way it's executed. Um, there are a couple things that SolidWorks Plastics has currently that we do not have on the platform, and some of that is some capability that is for a niche market. Say, birefringence is one of those things. Unless you're making lenses, you don't really even know what it is. So SolidWorks Plastics can do that. Um, there are some other capability that we now have uh, in the platform version of the simulation. But basically, they are the same. The results are very comparable. I mean, you compare one against the other, you can already see the difference. Some of that has to do with, there's a different meshing technology on the platform versus the meshing on the SolidWorks Plastics. But I think the big key thing is the ability to go into other platform applications, like um, the structural, uh, the structurals. If you're molding a conduit or whatever for air conditioning duct, You could go into a a flow calculation using some of the results. So you have available to you more simulation tools than you
Yeah.
do with
Well,
probably SOLIDWORKS.
and your mention of the cloud earlier. I mean, for one, like, to me, I think that's a major advantage for us to
Right,
be able to
right,
compute on the cloud. Like, if you don't understand what compute on the cloud means, that means you're not computing on your desktop. You're leveraging our cloud installation to do your compute on. And so now you don't have to have a really high end computer. And this works for all of our simulation applications, right?
right,
So now you
right.
can compute on the cloud, and you can run these high end simulations. And not have those needs of your computer power. I also did get a quick note from one of the experts that it seems like our warpage. I don't know if you know about the warpage, but I guess our warpage is more accurate in the software of 3D Experience as well. And I imagine that's probably just because of the general capabilities of simulation on the platform, including all of our Abacus technology and so forth, are more accurate for nonlinear behavior and
Yeah,
things
some
like
of
that.
those
So
the meshing tools
yeah,
too are important there. Yeah.
yeah. Well, hey, I just want to thank everybody. Most importantly, I want to thank you, Dwayne. Thanks for your time. Thanks for this awesome presentation. I really didn't know anything about injection molding, but I feel pretty good that I could go in there and make some really great predictions in there. It looks
I'm sure you
so
could.
so simple. Yeah, I can make predictions. We'll see if my assumptions
Right,
are
right,
correct. Garbage in equals garbage out, right?
right.
But yeah, everybody to the YouTube channel again. Thanks for coming back. Thanks for listening to us. We really appreciate the support. And speaking of support, if you haven't done so already, please remember to like and subscribe. It really helps us out so that we know you're enjoying the content we have. And send us some emails. Let us know. We're putting this information together specifically for you. And if there's particular content that we're not covering, let us know, and we can include that in the channel here as well, or we can go into more details or more depth as well. Next up in the series is where to place a GPS tracker on an e-bike. So we're gonna have some fun. So these next few sessions are we're really starting to reach into some of those advanced simulations, the questions that people have really been wanting to answer for quite a few years, and we just haven't had that capability. Injection molding's a huge one. So again, thanks, Dwayne, for that. And some EMAG, right? EMAG is the latest and greatest. So where would I put a GPS tracker on a bike so it can track all my physical heart tracking, my power output, the speed of my bike, where am I, all that kind of stuff. So we're going to go through some of that coming up in our next section. So again, thanks everybody. I appreciate it. Thanks again, Dwayne, and have a great day, everybody.